Hello friends, welcome again to the tetrahedron chemistry classes. So guys, it is my fifth lecture on IR spectroscopy. So far in my last 4 lectures, I have covered all the physical chemistry aspect of IR spectroscopy, right? Everything I have explained in the pretty much detail in my last 4 lectures. And today I am going to discuss, or today I am going to solve the previous year questions from the CSIR NET examinations. And these questions generally are from the physical spectroscopy part. Okay, so whatever right from the 2011 to 2020, whatever the questions in the CSIR NET chemistry have been asked in the based on the physical spectroscopy, right? Especially on the IR topic. Today I am going to discuss all those numericals. Okay, if you are watching video for the first time, so it is advisable to you, please go through the first 4 lectures. The link of all the 4 lectures are given in the description box, and if you are regularly following the lecture, then it would be very easy to understand these numericals today. Okay, so without wasting any more time, I am straightforward going to solve the question. And this questions actually I have taken from the June 2012 CSIR NET examination. And what it says that the following data were obtained from the vibrational fine structure in the vibronic spectrum of the diatomic molecules. That means you have been given a vibrational spectra, that means IR spectra of a diatomic molecule, and that from there you are getting the information like omega E, which is the vibrational frequency, which is given here 512 centimeter inverse, and this XE actually is the enharmonicity constant, and the multiplication with this omega E into XE, this value is given as 8 centimeter inverse. Now you have to find the dissociation energy dE for that molecule, right? So you have been given 4 options, so you have to identify which one is the correct. So to solve this particular question, right, if I am writing here the solution, okay, this is my solution. Okay, the formula basically which relates the dissociation energy and enharmonicity constant is dE equals to omega E divided by 4 times XE, right? So guys, in my last lecture, that means in the lecture number 4, I have made a mistake. You can see I have written the formula like that, and in the description box as well as in the comment section, in the pinned comment, I have made a correction for this actually. Okay, this you should note. So now the correct formula is this one, right? This is the correct formula, and in the previous formula you have seen I have written the 4 over there, which is wrong. Somehow I don't know how actually made this silly mistake actually. Okay, so you should avoid this. So now this is the exact formula. Now based on this, you know, the omega E is given. If you want to calculate the dE, right, omega E is given, which is your 512. Okay, you can write 512 like that, there is no problem in that, and then divided by 4, and you have to write the value of the XE. So you can very easily calculate the XE. How? You see, omega E times XE equals to 8 centimeter inverse, it is given. Okay, and omega E, as you can see, it is given 512. Okay, so instead of this omega E, you can write the 512 here. So if you write the 512 here, so it will become 512 centimeter inverse equals to, and times XE is already there, okay, and 8 centimeter inverse. So centimeter inverse and centimeter inverse, they got cancelled out, and the value of the XE is basically 8 by 512. Okay, so here you can see instead of this XE, you can write the 8 by 512. Okay, so you will write here 8 by 512, and this is given as centimeter inverse. Okay, this this is given as the centimeter inverse, right? So if you solve this value, right, if you solve this, then what you will get actually 512 centimeter inverse multiplied by 512 divided by 8 4s are 32. If you solve this, then you will get your answer 8192 centimeter inverse. Okay, so this is basically your answer, because I have already calculated this value, so I am not doing the calculations. So this here, right? If you check this, that means my option C is the correct option, right? So this is how you can solve this easy problem. The only thing is that you should remember the formula. If you don't remember the formula, right, then it would be very difficult for you to solve. Now this is my next problem, guys. This from December 2012 examination. The vibrational frequency and the n-harmonicity constant of an alkyl halide are 300 centimeter inverse and 0.0025 respectively. The positions in centimeter of its fundamental mode and first overtone are respectively. That means you have to find the fundamental modes of vibrations, the value in the centimeter inverse, and for the first overtone, right? And what you have been given, these things here. So I am writing the solution here. Omega E is given. This omega is nothing but it is your vibrational frequency. So sometimes see in the Banwell book it is written as the omega E, and I have written this as nu bar. Okay, nu or the nu bar, right? Omega E is the nu and omega bar is the nu bar. Okay, so this will not make any difference, but you know this is the vibrational frequency, and the value is given 300 centimeter inverse, right? And n-harmonicity constant is having the value of 0.0025. So you have to determine the fundamental vibration. So for fundamental vibration, if you consider the n-harmonicity also, then this will have the formula of omega E, or simply the nu bar 1 minus 2 of Xc. This is the formula which I have derived in my last lecture also. So omega E is 300, okay, 300 centimeter inverse, 1 minus 2 times 0.0025. okay, that means it is giving you 300 1 minus 0.005. okay, so this actually not like just like that, it is given like that. Okay, and if you solve this, then it will give you 300 times 0.995. If you multiply all these things, 3 5s are 15 here, 3 9s are 27 and 28, 3 9s are 27, 28, 29, 2985, and since 3 decimals are there, so 1 2 3 here you can write, you can count here 1 2 3. okay, so you will put decimal here. So your fundamental modes of vibration is somewhere around here, this 298.5. so check where it is given. So this cannot be your answer, okay, but this can, see, this is 298.5, this could be your answer. So there is no need to solve further. Okay, so option B actually is the is looking the correct option. But if you want, then you can also calculate for the first overtone. So for first overtone, formula is 2 of omega E 1 minus 3 of Xe, right? This is the formula, and then you can put the value 2 into 300 1 minus 3 times 0.0025, and that will give you 600. 300 into 2, that is 600. 1 minus 0.0075, that will give you 600 times 0.9925, and that will give you 595.5, right? So this value is given here. Okay, so this is the correct option. So option B in that case is the correct answer. See how easy these numericals are actually. But nowadays they are not actually asking these kinds of the simple problems. But see, I'm not saying that they are not asking. In fact, they have asked the same kind of the problem in the 2020 examination, right? That means November examination, right? And now if we go further, then what is my next problem? The chemical reactions involving a non-linear molecule and another non-linear molecule, and they are forming the non-linear activated complex, and finally it will give you the product the number of the vibrational degrees of freedom in the activated complex containing n atom is. So this problem is actually not straight from the IR spectroscopy, but it is the amalgam of the IR spectroscopy and the chemical kinetics. So I haven't actually uploaded any lecture about on the chemical kinetics, right? So but I am telling you, if you learn the transition state theory, right? If you learn the transition state theory, then in the transition state theory it is clearly states that whenever such kind of reaction is happening where non-linear and non-linear, they are actually combining to give you the non-linear activated complex. So one of the vibrational degrees of freedom actually being converted into the translational degrees of freedom, right? So if you have say certain values of the vibrational degrees of freedom, so out of those vibrational degrees of freedom, one will convert into the translational degrees of freedom. That means you have to subtract the value of the one vibrational degrees of freedom from the formula of the vibrational degrees of freedom for the non-linear system, right? So if you solve this, I am writing solution here, and you know 3n minus 6, it is what it is the formula for the vibrational degrees of freedom. I am writing the VDF but as you know, in the transition state theory, it clearly states that when your molecule is converting or is forming a non-linear activated complex, then one of the vibrational degrees of freedom will convert into the translational degrees of freedom. That means you have to subtract this value 1 from here, and when you subtract this, then you will get the 3n minus 7, right? So this is your correct answer. So option C you can mark, right? This problem is very easy. And then my next problem, what it says that the spectroscopic technique by which the ground state dissociation energy of a diatomic molecule can be estimated is, right? So what it is saying, it is a very simple problem. Though I haven't written the different kinds of the spectroscopic technique, but if you have followed my previous lectures, or you are aware about the IR spectroscopy, then it is very easily you can conclude that the ground state dissociation energy can be calculated by the vibrational spectroscopy. So IR spectroscopy for this is the correct answer. Okay, so you can write IR spectroscopy or vibrational spectroscopy. This will give you the idea. Now moving to the next problem, what it says that from the December 2015 examination, what it says that if the reduced mass of a diatomic molecule is doubled without changing its force constant, the vibrational frequency of the molecule will be, right? This is actually the simple problem, but you have to do little bit of your junior class mathematics to solve such kind of the question. So how we can solve this question? And please remember what the question is saying, that this force constant, that is K, is not changing, right? That means K unchanged. Only reduced mass is actually changing. So here you can make two equations, like nu1 equals to 1 on 2 pi force constant divided by reduced mass, right? So this is for actually your first case, okay, nu1, and this is one of the form of the Hooke's law. You can write like that, okay. Say this is your equation number 1, and similarly you can write nu2 equals to 1 on 2 pi. Again you will write K because force constant is not changing, then you can write mu2. Say this is the equation number 2, okay, and then you can take the ratio, right, from equation 1 and 2. So that means nu1 over nu2. So you can write nu2 over nu1 also. This will not make any difference actually. What it will give you for nu1, 1 on 2 pi, you can write like that, and this is your K over mu1. This should be divided by 1 on 2 pi under root K by mu2, okay. So what you can do here, you can cancel these two, okay, and you can cancel K also. And when you do this, then you left with the under root of mu1 not mu1 actually, sorry, under root of mu2 over mu1. Why I did that? See, this mu2 in the denominator, so this will go up, and here also this mu is the denominator, this will come down. That's why mu2 by mu1. Okay, and then you can put the values here. How you can put the values? What the question is saying? Question is saying that reduced mass of a diatomic molecule is doubled, right? So you are taking the second reduced mass is the double of the first one. Okay, so this you can see here. This is your mu2, which is the second reduced mass, and which it is the double of the mu1. So here you can write 2 of mu1 and mu1 over there. So you can cancel actually here this and this, right? So what you left with? You left with like that. You have to calculate what? You have to calculate nu2, right? You have to calculate this nu2. So I made a little mistake, not mistake actually, I make the question little bit typical, right? So because I have divided equation 1 with the equation 2, but you can also do like that. You can divide equation 2 by the equation 1, but it will not make any difference in the final answer actually, right? So I am inverting it. I am writing nu2 by nu1 sorry, that is equals to under root of 1 by 2, right? So I'm making the reciprocal of this, right? So that's why if I invert this, then automatically they will also invert. So it is under root 1 by 2. So here, from here you can conclude mu2 sorry, it is what? 1 by 2 of nu1. So this is basically your answer. So here you can write what option actually is correct in that case, right? Here 1 by under root 2 of the vibrational frequency. So this is 1 by under root 2 of the vibrational frequency. This is how you can solve the problem. See, this kind of problem actually I have already solved in my second lecture, I think. If you go there, then I have solved this kind of the problem, not exactly this problem, but this kind of the problem I have solved. Okay, so nu2 is basically your 1 upon under root 2 of the nu1, which is the original frequency. Nu1 is the original frequency, right? So that's why 1 by root 2 of the vibrational frequency. Now moving to the next problem, what it says that the vibrational frequency of a homonuclear diatomic molecule is nu. The temperature at which the population of the first excited state will be half that of the ground state. Okay, that means it is clearly indicating that you should use your distribution law. Okay, so how we can solve this problem? For this you need to know what is actually the distribution law. So I am writing the solution here. Population in the second state over population in the first state, that is equals to e to the power of negative h nu by kt. This is the exponential form. Okay, there is no problem in that. And what the question says that the vibrational frequency of a homonuclear diatomic molecule is nu. The temperature at which the population of the first excited state, that means say nu2, will be half of the ground state. See, if this is the ground state and this is the excited state, that means this would be half of this one. Okay, that means this parameter is given in the question itself. So you can write n2 n1, right? And this would be what? See, n2 is what? Half of the first state, that is n1, and oblique n1 is already there, so you can cancel them. N1 and n1 you can cancel them, and this will give you the 1 by 2. So n2 by n1 is your 1 by 2. This is given to you. Okay, so here what you can do, you can write 1 by 2 in place of this n by 2. Okay, there is no problem in that. So I am suffering from cough and cold for the last few days. Sorry for this. That means e to the power of negative h nu by f kt, right? This you have written. So now this is the exponential form, guys. And if you are a biology student, right, and you don't know what is the exponential form, how we can convert the exponential form into the log form, then obviously you will have the problem in solving such kind of the problem. So it is my personal advice to the students of to the biology students actually who left the mathematics after 10th. They actually should actually practice the basic mathematics, like mathematics up to from 1 to 10th mandatory, and your calculus, your matrix, your vectors, all these things, right, for the 11th 12th part also. Only then you can understand, or you will be able to learn the physical spectroscopy or the physical chemistry. And without the at least up to mathematics of at least up to 12th, right, it is very difficult to understand the physical spectroscopy, right? So this is very important. So now I am changing this into the log form. Okay, so I am writing here changing into log form. What I can do, I can take the log on the both side. So this will become natural log of 1 by 2. Okay, and since I have taken the log, that means this anti-log term will eliminate from here, and you left with minus of h nu by kt, right? Up to this problem, up to this point there is no problem. Okay, and then you need to determine the T, actually the temperature, so you can adjust this equation. So how you can adjust this equation? I am writing here. So this is log of 1 by 2 multiplied by k over h nu equals to negative of 1 by t. What I did actually, I shift this part actually, right, this h nu and k from here to here, right? So this k will go up and this h nu will come down, right? This is the general mathematics, right? And then because I need the t, so I'll reciprocate. So instead of t I can write minus t. Okay, and that will actually invert the expression on the left hand side also, h nu over ln of 1 by 2, and that should be multiplied by k. Okay, and if I change the sign, then I will get my answer T equals to h nu log of 2 of k, right? For this you need to understand, see, actually log m by n equals to log m minus n. So that's why if I'm changing the negative sign from here and making it positive, and I put the negative sign here, that means this log part will change and this will become ln 2 of k. So let's check whether this option is given in the given options or not. So this h nu is there, over log 2 of k. K or kb both are the same thing, right? Distribution coefficient. So this is your correct answer. That means option B is the correct answer in that case. I hope you understood the problem actually, right? Now moving to the next problem, what it says. Okay, vibrations of the diatomic molecules are usually modeled by the harmonic potential. Okay, this is fine, this is basic principle. If the potential is given by the kx square, the correct statement is, okay, again this problem is based on the simple mathematics. What the question says, so I am writing the solution here, guys. But question is saying that vibrational potential is given as x square. This is the question, which is with the C. If the potential is given by x square, so you can write the V equals to x square. And since it is changing, it is the, see, this potential is the function of this actually x, which is the displacement actually. So you can simply apply the mathematics or the calculus to this, right? So what you can do, you can write del V over del x, because it is the function of this, that is equals to del or del x, and instead of the V you can write x square. This is x square. Now if you check the maths corner of this one, you know I can write here math corner for the biology students. This formula is simple: d by dx of x equals to, or you can say the x to the power f n x n minus 1. This is the formula which you should use here, right? So for this you can write here, if you solve this, so this would be 2x 2 minus 1 equals to 2x. So that means your v equals to 2x. So let's check v equals to 2. See, in option A, force is the 2x here, and force is the 2x, and C, k is the 2. So this is actually not solving the problem, so we have to move further actually, right? If you are stretching, see, I already told you, if I am stretching the your bond, then the force will apply in the opposite direction, right? This is I explained in my very first lecture. So we know the restoring force is always in the opposite direction of the stretching. Okay, so in that case your force would be minus 2x, right? This is the potential. That means stretching you are doing, you are applying this much of you are stretching your spring or the bond in that manner, and the restoring force would be in the opposite. If you are stretching the bond like that, then the restoring force would be in the opposite direction. So if it is 2x, then the restoring force would be minus 2x. So let's check. Force is 2x, so this cannot be your answer, guys, because it is minus 2x. Force is minus 2x, so this B could be the answer. So what you can do, you can eliminate the option A, or you can take this one. This may be your answer. You can eliminate this one and you can take this one. So here B, or either B or D, both actually may be your answer. For this we have to solve this question further. So how we can solve this question further? Say for example, you know vibrational frequency is given by about half of kx square. This I have explained in my very first lecture. Okay, say this is the equation number 1, and what is given in the question? V equals to x square, right? This is equation number 2. So from equation 1 and 2, what you can write? So I can write here, from equation 1 and 2. So V, for V you can write x square. So I am writing x square, and that is equals to half of kx square. So from here you can get your value of k. So that will give you 2x square over x. They will cancel out. K equals to 2. Now here you can see in the option B, force is the minus 2x, but force is 2. So this is the correct answer. Here force is the minus 2x, but force constant is minus 1, which is not correct. So you can safely eliminate the third one also. So this is your correct answer. Option B is the correct answer, right? So but for this you need to know the little bit of the mathematics. Now moving to the next problem, what it says that, okay, from the June 2018 examination, assuming harmonic approximation, the energy change for the reaction HCl plus deuterium, that is forming deuterium chloride plus deuterated hydrogen, that is HD, okay, and in centimeter inverse. And in the question it is given that the vibrational frequency of HCl, vibrational frequency of D2, vibrational frequency of DCl, and vibrational frequency of the HD. Basically this question is not from the IR spectroscopy. This problem, see, such kind of the problem you have already solved in the thermochemistry, right? So this is very basic problem, but they somehow actually mold this this question to the IR spectroscopy change, right? So how we can solve this question? See, epsilon V, that means vibrational energy, and vibrational energy is nothing but it is the half of the summation of the energies of the product minus summation of the energies of the reactant. Okay, so in that case you can see these HCl, they are the reactant, so you can write half of E HCl plus, so sorry not E, very sorry, these are the reactant and these two are the products, so I have to take the products here. So you can write E of DCl plus E or epsilon of your HD, okay, then minus epsilon of the reactant, and your reactants are HCl, that means this of HCl plus epsilon of D2, okay. So basically this problem is like that. So now it's very easy, half bracket start, and for you can see here for epsilon DCl, so DCl it is 1990, so you can write 1990 plus for HD this is 3627, so you can write 3627, okay, and then minus epsilon of HCl which is given 2885, so you can write 2885 plus epsilon of D2 is 2990, bracket close, and that will give you half of, if you add these two, that will give you 5617 minus, if you add these two, this will give you 5875. So if you solve this, this will give you minus 258, half of this 129 with negative sign, of course in the centimeter inverse. Now let's check. This cannot be your answer, this cannot be, minus 129 as your answer, so this is the correct. Option C is the correct answer in that case. Now moving to the next problem. It is again from the June 2019 examination, and what it is saying, what the problem is saying, the correct statement about HCl and DCl among the following is: DCl has a smaller 0 point energy than the HCl. HCl vibrational frequency is smaller than the DCl. Okay, so this actually this problem actually is not the kind of the problem which you can solve by only examine the options given. You have to solve this question. So I am writing solution. How we can solve this? You know, see guys, one thing you should know actually, reduced mass is what? See, reduced mass is summation of the, multiplication of the two masses involved in the diatomic molecules, okay, divided by sum of these two. And you know, in this question hydrogen is given and deuterium is given. So your deuterium is heavy. If your deuterium is heavy, that means one thing is quite clear actually. DCl reduced mass, DCl, mu of DCl would be greater than mu of HCl, right? And formula you know, nu equals to 1 on 2 pi k of mu. That means this mu is inversely proportional to the vibrational frequency. If your DCl is having higher reduced mass, then its vibrational frequency would be low. So first of all you need to check in which case actually DCl vibrational frequency is lower, right? We have to check this thing, right? This is something very, very important. DCl has a smaller 0 point energy, so we cannot actually see what is the 0 point energy. Let's check what is the 0 point energy. 0 point energy is nothing but E0 equals to V plus half of nu bar, this is 0, this is 1 by 2 times nu bar, that is half of nu bar, so this is the 0 point energy, right? And I already told you that means the vibrational frequency would be lower for your DCl, so that means your view DCl is lower. Let's check the nu bar DCl is lower where. Let's check. DCl has smaller 0 point energy than HCl. Yes, this is quite correct, guys. So option A, right? If you check, the option A is looking the correct option, but let's examine other options given also. HCl has a smaller vibrational frequency. No, no, no. Why it cannot happen actually? Because vibrational frequency actually vibrational frequency is governed by the reduced mass, and reduced mass is lower for this one. That means for this it should be higher actually, right? So for this HCl should be higher, or energy for this should be low. So first one is correct. Second one is actually not looking the correct option. Force constant of the HCl is just half of that. This one, no, this is also not correct, because force constant is directly proportional to the vibrational frequency, and you know the vibrational frequency is lower for this one, right? That means it's mu. That means for DCl your vibrational frequency would also lower, and your vibration constant is also lower. And here it is saying that it is half. No, it is not like that. It is actually not half. The reduced mass of the DCl is lower. No, no, no. DCl, deuterium is heavy, right? So this is also not correct, right? So this is the very good problem. You actually, if you have learned the concept of the IR spectroscopy in the pretty much detail, and you understood the things very well, only then you will be able to solve such kind of the answer, right? So therefore, see, DCl actually will have the lower 0 point energy, right? This is quite clear from here. Now moving to the next problem. The vibrational transition energies of diatomic molecules corresponding to nu 0 to nu 1. Here transition is going from nu 0 to nu 1. Here transition is going from nu 1 to nu 2. So from nu 1, in the last class, you know, whenever you have the excess population in the nu 1, the only condition is that you are doing this at the higher temperature. So this is basically hot band. This is hot band. This is your fundamental vibrations, and the vibrational frequencies are given for the fundamental vibration and your hot band, right? And you have to calculate the n-harmonicity constant, right? Again, this is see, very simple kind of the problem, not a very big deal in that case, but you need to understand the concept of the hot band and fundamental bands, right? Overtones, all these things. So here, whenever this transition is here, V equals to 1 and V equals to 0, this is your fundamental transition, fundamental. And for fundamental transition, you know what is the energy, right? Energy is given by del E equals to nu bar 1 minus 2 of XE in centimeter inverse, right? And if your transition is happening from like that, from V1 equals to V2, okay, then it is your hot band. Though I actually didn't calculate the energy difference of the two the levels of the where actually two levels where you are actually where you can observe the hot band. But if you know the concept, then you will be very see, it is very easy for you to calculate this energy difference also. So for this, del epsilon equals to 2 nu bar, okay, and not 2 actually. In that case, we cannot put 2 here, I think. Not 2, nu bar only. In case 2 is actually is your type of the overtone, and you can write 1 minus 4 of XE. It is in centimeter inverse, right? So if you want, then you can calculate also, right? But I am not going to calculate, because in my last lecture I have already given you the concept actually how you can calculate, right? So first of all, if you actually make equation for V equals to 1, then make another equation for V equals to 2, including your n-harmonicity constant and all these things. Then subtract the value of the E2 minus E1, then you will get this result, right? You can do you can do yourself actually. If you are finding difficult to solve this thing, then please comment in the comment section. I'll actually then I'll explain in the separate lecture also. But right now you can understand in that manner, okay? And for this, you know, for this fundamental vibration, this energy is given, right? And for this overtone, this value is given here. So here you can write these things. So you can equate these two equations. See, you can not equate, you can write these two equations. So instead of the del E, you can write 2, 1, 4 3.1. This is for fundamental vibration. So you can write nu bar 1 minus 2 of xe. Of course it would be in centimeter inverse. And then you are having next value 2116.1. that would be for your hot band. For hot band, nu bar 1 minus 4 of xe, it is in centimeter inverse. So you can cancel them. Okay, how? Change the sign. So make it negative, okay, and then make it positive. Okay, just like that. Then you can then you will be able to solve this and make it negative. So if you take the difference of these two, right? If you take the difference of these two, then this difference is 27, I suppose. Say I haven't solved this problem, so it will take little bit of time actually, right? Because I haven't solved this problem. 0.10720, okay, 27.0. So it is 27, okay, 27.0. And then this new gets cancelled, 1 and 1 gets cancelled, and then you will get the 2 of xe, because you see 4 minus 2, that will give you 2, and xe is already there. So then your xe equals to 27 by 2, that will give you 13.5 centimeter inverse. Let's check whether it is given or not. That's 37.5. Here you can see that 37.5, option B is the correct answer. So this is how you can solve the problem. Now moving to the next problem. What it says, okay. The equilibrium dissociation energy of a diatomic molecule is 4.75 electron volt. Okay, it is not given in the centimeter inverse, and its stretching frequency correspond to the 0.5 electron volts. Right, so minimum energy required to dissociate the bond. Actually, this problem is based on your Morse potential. Right, so for this you need to know the Morse potential curve. And see, in my earlier lectures, I already explained you how you can write the Morse potential and all the equation. So let's actually recapitulate. For Morse potential, this was the condition, this was your internuclear distance, okay, this was the energy in the centimeter inverse, and Morse potential is going like that. And then you know, if you start from here, this was the condition of the Morse potential, okay, and say if it is V equals to 0, it is 1, it is 2, and so on. So this actually is what here, if you take this part, so this distance is basically what? This is your bond dissociation energy DO, right? Which is actually I have taken from the lowest point, that means 0 point energy, right? Lowest curve, right? From here actually. So lowest curve what I did, see, I made a mistake. Yes. Now it is quite fine, okay. And you know, this distance is basically your DE, experimentally find dissociation energy. D is not experimental. DO is the experimentally find dissociation energy, and DE is the dissociation energy of the molecule, which I reckoned from the lowest point, right? Lowest point is here actually. So this thing you need to understand, and this actually I have to find. This value I have to find actually, okay, and this value is nothing but it is 0 point energy, right? Like that. So if you check this, right, so basically this DE, right, if you write this DE, so this DE is having two things. So first is your DO and remaining is your E0. So that means DE equals to D0 plus E0, and you need to find D0, dissociation energy, right? You need to find dissociation energy. That means DO equals to DE minus E0. Experimentally find dissociation energy is given. The equilibrium dissociation energy, that is 4.75. It is given in the question itself, guys. So you can write 4.75 minus, then what is given, this 0.5 actually is the stretching frequency corresponding to this one, right? 0.5. That means which is this one. See, it is having the lowest energy, right? Lowest vibrational energy. Even if you keep the sample at the absolute zero, then again you add absolute zero also, your molecule will vibrate actually, right? So this is the actually the stretching frequency or the vibrational frequency, right? And it is having the value of 0.5, both in the electron volts. That means 4.50 electron volt should be the answer. Let's check. 4.75 no, 4.25 no, option C yes, 4.50, option C is looking the correct answer, right? So this is how you can solve the problem. So I have solved all the physical spectroscopy part of the IR, and see guys, actually problem solving skills are very, very important, because sometimes it happens that you actually don't understand, or see, it is very difficult to understand the theory, but once you solve the numerical based on the concept, then it would be very, very easy to understand the theory part also. So basically numericals gives the deep insight of the theory. That's why it is my personal advice to all of you, whenever you are learning any kind of the topic, any topic in the chemistry or physics or in any subject, actually don't only focus on the theory part, always go for the numerical part, reasoning part, all these things. So this see, today I have explained this numerical part. In some other lecture I will also explain you the reasoning questions actually in the IR spectroscopy, basically the interpretation part. So in the next class I will start with the interpretation of the IR spectroscopy, IR spectra, and I'll give you the separate lecture for this, like for alkane I will explain the things in the detail, then for alkene and all the functional group which are there actually, for which actually we can record the IR spectra. I'll discuss their interpretation in the pretty much detail, as I did for your proton NMR spectroscopy, mass spectrometry. For all these things I have done all the things in the detail, and I'll do for the IR interpretation of the IR spectra also. So that's it for today, and if you are watching for the video for the first time and you understood the concept, then please like the video and share the tetrahedron chemistry classes content with your friends also, okay? And if you are not if you have not subscribed my channel yet, please subscribe the tetrahedron chemistry classes. So that's it for today. Thank you. Thanks for listening.